Hi calculus students! In this video we're going to continue on where we left off in lesson 2. So previously we learned about the properties of limits and just kind of how to add, subtract, multiply different limit values together. In this video we're going to do the second part, which is the algebraic manipulation, which means we're going to have actual equations that we're finding the limits for. Just a heads up, we have way more algebra to do in this video, okay? So far we haven't had to do much algebra. Now's the time when we get to do it. So just giving you a little warning. So here is what we did last time with our properties of limits. Notice here that we always just had kind of generic functions like f of x and g of x. Like they never gave us actual equations for the functions, they were just in general. And that's what's mainly going to be different. Okay, so when we're solving limits algebraically, there's kind of 3 different levels of steps that you're going to take. And here's a table I made for that. You can pause and copy this down right now. I'm also going to go through each of the different options with examples. So it's kind of up to you whether or not you just want to write the whole table all at once or wait as we do each part with the different examples. I'll leave that up to you. So let's go. Let's see what each of these looks like. Okay, so case 1. And remember, for each of these, we're looking at this as though we're solving the generic, the limit as x approaches a of f of x. Okay, so this is the limit we're trying to solve. Okay, so what we're going to try to do for each of these is just try to evaluate f of a, okay, which means we're just plugging in the value of the limit that we're approaching, the x value that the limit is approaching, okay? So let's just do that for these limits. So here, the limit as x approaches -1 of this big function, I'm just going to try to evaluate f of -1. So f of -1 will equal -1 squared minus 4 over -1 squared plus -1 minus 12. Just a quick algebraic note, you probably noticed that I put the -1 in parentheses when I was squaring it. Very important, don't forget those parentheses because that will turn -1 squared into +1. I'll write -1 minus 12 is -13. So this is -3 over -12, which is equal to +1/4. I got a number, so I'm done. Hooray! So here is where you can see the limit as x approaches -1. Can't really get a point. There it is. So at -1, the value of the function is equal to 0.25, which is 1/4, which is what we got. So this case where it will happen, where if you just plug in the number, you get the limit, that's when you have a nice function at that point that's continuous, there's no holes, there's no vertical asymptotes or anything like that. And so just visually, this is what it will look like when you're able to plug in and just get a number. It means at that point, it's continuous and nice. B is very similar, it just has the added challenge of being a piecewise function, so you have to be more careful into which function you plug into. So just a reminder of how piecewise functions work. Here we have our different functions, and these are called my domain restrictions. So the domain restriction basically just tells you which function you can plug which values of x into. Okay. So here it also is showing me that I'm looking at the limit as we approach 2 from the left. So that means we're coming from numbers less than 2. So I'm going to highlight this right here. So 2 from the left means we want numbers less than 2. So that is going to be the function that I use. F of 2 in this case, since I'm using that top function, will be 3 times 2 minus 7, which equals 6 minus 7, which equals -1. So there's the limit for when x is less than 2, or when x is approaching 2 from the left. So this is kind of the best case scenario. Okay, so in case 2, this is when we could get other things like 0 over 0 or infinity over infinity. And so these values right here are called indeterminate forms. There's a little vocabulary for you. It's an indeterminate. When you think of that word indeterminate, it means like, I'm not sure. I can't determine what that means. And so when you get an indeterminate form, it means we have to do something with the equation in order to make it solvable. We can't determine the limit at this point. We have to do some more work in order to make it solvable. So this is where a lot of your algebra is going to come in. And so like here are the things you might have to do: factor and reduce, rationalize the numerator and denominator. This one I'm going to put in parentheses because we're not going to be able to do that for a couple more months. So that is just something that in the future you'll know what that means. We might have to use like our trig formulas, or if we have access to a graphing calculator, we could use a graph. Oftentimes this will be on the non-calculator enabled section. Okay, so let's see what this looks like in practice. So we're going to do the same thing as before. We're just going to plug in the number and see what we get. So this is, well, I'll say f of 3 equals 9 plus 3 minus 12 over 9 minus 6 minus 3. With quick mental math, this equals 0 over 0. So I got an indeterminate form. So that means I need to do some more work before I can actually solve this problem. So it looks like I can just do that first step of factor. Okay, this looks very factorable, so I'm going to try to do that. So I'm going to rewrite this as the limit as x approaches 3, factoring the top, x plus 4 times x minus 3. Yeah, hopefully over your summer packet you practice your factoring skills. And then the bottom looks like it's x minus 3 times x plus 1. Cool. And look what happens. So the term that made this 0 over 0 is right here. X minus 3's, because if you think about, if I plug in 3, I get 3 minus 3 over 3 minus 3. That's 0 over 0. So we're able to cancel that term out, and that will make it possible for this function to no longer be 0 over 0. So now I have x plus 4 over x plus 1, and now I can plug in my value. This is equal to 3 plus 4 over 3 plus 1, which is 7 over 4. And I have a limit value now. So what this looks like on the graph is right here. So the limit as x approaches 3, I bet at that point it's undefined, and you can see how there's like a little hole there. This is a hole. This is why you have holes. So this is kind of explaining on the graph, like, what the heck, why are there holes? This isn't explained. It's because it's a point in the graph. Where'd it go? I keep losing it. It's a point in the graph where you're able to kind of cancel out. If I were to just plug in 3, I get that indeterminate form. I get 0 over 0. And so it's a point on the graph that cannot exist in this equation. So at x equals 3, the graph is undefined because I get 0 over 0. But everywhere else it's fine, and I can see that the limit from the left and the right equals that 7 over 4, which is a little less than 2. You can see that on the graph. So visually, graphically, that's what that looks like. When you're able to factor it out like that, it's a whole. Okay, so I'm gonna actually add a little note. So f of x has a whole at x equals 3. So just a little note for yourself. B looks like something I can factor as well. So, well, I mean, we could always check. We could check to see if we can plug in. If I plug in -2, I get 4 plus 4 minus 8 over 4 minus 4. That's 0 over 0. That's an indeterminate form. So I know that didn't work. Plugging in didn't work, so let's try factoring. That didn't work. So factored, the numerator can be factored like this, and the denominator is what's called a perfect square. So that means I can take the square root of x squared, I can take the square root of 4. It looks like this. Perfect square. And look, the thing that caused my issue can be canceled out. So if I were to try to plug in -2, I'd get -2 plus 2, that's 0 over 0, but I can cancel that out. So again, I know that there's actually a whole at 2. So f of x has a whole at x equals -2. But we can cancel that out with our factoring. So now this is equal to the limit as x approaches -2 of x minus 4 over x minus 2. Now when I plug in -2, I get a -6 over -4, which equals 3/2. So about 1.5 is the limit. Let's look at this thing graphically. It's this one right here. So at -2, it should become undefined. See? There. Got it. So it's undefined. There's a whole at -2. But I can see if I get really close to -2, it equals about 1.5, which is right there. The limit is -2. The function value is undefined. Cool. And then we're gonna do one with a square root. So this is like what the rationalizing looks like. The other two examples were examples of factoring and reducing. Okay. So this is rationalizing. I don't know if you've heard of, I'll just get rid of all those lines, rationalizing before. This little square root here is called a radical. Square root is also called a radical. So rationalizing means getting rid of the radical. So the way to get rid of a radical is to multiply by its conjugate. Okay? So I'm just going to add that vocabulary for those who aren't familiar with it. So we're multiply by the conjugate. Okay, so what the conjugate is, it's basically I take the same number, but instead of that -2, I'm going to say +2. So I take the same term and I just change that a little bit. And I do that to the top and the bottom. So basically I'm just multiplying this by 1. I'm not changing the number since I'm multiplying the top and the bottom by the same thing. I'm multiplying by 1. That's totally legal in math. But what happens here, I'll show you all the math, but eventually when you do this, you don't have to. So when we multiply out, basically we're doing that FOIL. And so this 2 square roots will cancel out. If you multiply 2 square roots, the square roots just cancel out. So I get that x plus 6, and then multiply, oh no! I wanna multiply the square root times +2. So that will be positive 2 times the square root of x plus 6. And then over here, negative 2 times the square root will be minus 2 times the square root of x plus 6. And then negative 2 times positive 2 is negative 4. And I'm still taking the limit as x approaches negative 2. Okay? That's like the majority of our algebra. And you can learn a shortcut for that. The bottom, I'm just going to keep the same, and you'll see why. So I'm not going to multiply the bottom out. I'm just going to keep it like this in its factored form. So I'm not going to multiply the bottom out, only multiply the top. So you could probably see that some of this junk cancels out. So these two terms go away. They cancel each other out. So the numerator is just left with this. Okay, so we have the x plus 6 minus 4. And that's like the whole purpose of multiplying times the conjugate. It's kind of like a perfect square, actually. Like over here, when I have the perfect square, x plus 2 and x minus 2 are conjugates. And so what I'm just left over is x times x and 2 times negative 2, which is x squared and negative 4. So it's this, those conjugates kind of show you how that might look like. So really, I can skip all the stuff in the middle because these two things just cancel each other out. And I'm just multiplying the square root of x plus 6 times the square root of x plus 6 and negative 2 times positive 2. And I get that. Okay, so it takes practice. But if you practice enough, you'll be able to just kind of figure out the pattern. Okay, and I still have this long thing at the bottom. You'll see why I'm not canceling it out. And it's because if I look at my numerator, I get x plus 2. And then I have my x plus 2 in the bottom. And that x plus 2, oopsies, is exactly what I wanted to cancel out. Because my limit is going to x minus 2. So when the x plus 2 cancels out, I no longer get 0 over 0. So just like we did before with the factoring. So these cancel out. I no longer have the thing that gives me 0 over 0. So the numerator is 1, and I'm left with this little conjugate down here. So whenever you're rationalizing, it should end up really nice where these things cancel out. If that doesn't end up happening, you made an algebraic mistake. So this should always work out nice where what you want to cancel out cancels out. So now I can finally plug in my negative 2. And I get 1 over the square root of 4 plus 2, which equals 1 over 4. I know that's super ugly. Students generally hate it, but yeah, we gotta do it. So graphically, that looks like this. So the limit as x approaches negative 2 is undefined. There's a hole there. Luckily, we're able to factor out that term, that x plus 2 term. And so the limit, we got 1/4, and you can see as I get really close to negative 2, it's approaching, the limit is approaching 1/4, or 0.25. Cool. So also, I'm showing you the Desmos to help you understand, like, you have access to Desmos too, and you should definitely use it to help you check your answers. So I do expect you to do these algebraically, but always check on Desmos. Okay, so then here's our third case. Remember the second case? You could do these algebraic steps whenever you got 0 over 0 or infinity over infinity. Those were called indeterminate forms. The next one is if we get not 0 over 0. So basically, if I get some number like 5 over 0, or negative 3 over 0, or 253 over 0. And what's happening here, if you get any number over 0, is that there's a vertical asymptote. Okay, so that means it's not a hole, like in the previous case, it's not a hole. So back here, these were all like holes in the graph. This has an asymptote. And so just a reminder, asymptotes happen when you have your little reciprocal functions. And so there's a couple of options for what this could look like. So the three answer choices are going to be positive infinity, negative infinity, or does not exist. And the way to get those three just kind of depends on where your asymptote is. So to get positive infinity, that just means at wherever your asymptote is, the graph are both going to positive infinity. To get negative infinity, that means wherever your asymptote is, I'll draw it over here now, there's my asymptote, it means the graph is going to negative infinity. Okay, so for positive infinity, the graphs are both going up. For negative infinity, the graphs are both going down. And then for does not exist, that just means wherever the asymptote is, the graphs are going in different directions. So that means they're going different ways. Okay, one's going up and one's going down. So anytime you have a vertical asymptote, when you have not 0 over 0, this is what's happening. So let's look at our first example. If I were to plug in 2, just plug it in, I'd get 2 times 2 plus 5 over 2 minus 2, which equals 9 over 0. So I got not 0 over 0. I know that there's a vertical asymptote. And the vertical asymptote is at 2. So I'll say f of x has a vertical asymptote at x equals x equals 2. Okay? So this is just a regular 2. So I need to determine at my asymptote, are the graphs both going up, are they both going down, or are they going in different directions? So that means I need to check out the function from the left and the right. Okay, so I'm gonna find the limit as x approaches 2 from the left of f of x, and I'm gonna find the limit as x approaches 2 from the right of f of x. Okay. Okay. So the limit as x approaches 2 from the left, basically I can just plug in a number that's smaller than 2, but still really close to 2. So I can plug in like 1.9. Like that. And basically I just need to know, is this number going to be positive, negative, or negative? Sorry, positive or negative? Because all I could care about is it going up or is it going down? Right? I just care about the direction that it's going. So 1.9 times 2, that's, sorry, 3.8 plus 5 over negative 0.1. I don't really have to do all the math here. I can see that this is going to be a negative number. So it's going to a negative number, negative infinity, because I have a positive over a negative. And then over here, I can plug in a number a little bit bigger, so I'll plug in 2.1. I'm looking at the right. So that's 4.2 plus 5 over 0.1. I can see that this is going to positive infinity. So from the left, my asymptote, to the left of the asymptote, my function is going down. to the right of the asymptote, the function is going up. So this overall limit, the limit as x approaches 2 of f of x, does not exist because they're not going the same way. And let's look at this graphically. So I can see at 2, there's an asymptote. There's an asymptote at 2, and again, the limit from the left goes to negative infinity, the limit from the right is going to positive infinity. Okay, we figured it out algebraically, but I can check it on Desmos. So you can always check your work on Desmos. Let's look at another example. So again, if I were to just plug in 3, I would get 3 over 0. There's an asymptote there. So f of x has a vertical asymptote at x equals 3. So let's find the limit as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right of f of x. Okay, so from the left, I'll just plug in a number slightly smaller than 3. That's 2.9 over the absolute value of 2.9 minus 3. So that will be 2.9, and 2.9 minus 3 is negative 0.1, but the absolute value will make it positive. So this is going to positive infinity. So pay attention to those absolute values. And then the limit as x approaches 3 from the right means we need a number slightly bigger. This is also going to positive infinity. So since the limits from the left and the right are both going to positive infinity, I can say that the overall limit as x approaches 3 of f of x is going to positive infinity. And again, let's look at this graphically. Here it is. So at 3, you can see that there's an asymptote, but from the left and the right, they're both going to positive infinity. This is going to happen a lot when you have the absolute value bars. So the absolute value bars, instead of getting a negative and making them go opposite, will turn it to positive. Okay, oopsies, didn't mean to do that. And now let's look at our last example with a piecewise function. So the limit as x approaches 2, I can see for both of these equations, the denominator is going to be equal to 0 and the numerator is going to be equal not 0. So there's some sort of asymptote there. Which means, so I can say f of x has a vertical asymptote at x equals 2. And now let's look at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. So the main thing with this piecewise function is just make sure you're using the proper equation. So the limit from the left means I'm looking at values smaller than 2. Okay, that means I want to use this bottom equation for the limit on the left. I'm using the bottom equation for the limit on the left. So that will equal like 2.9 minus 3 over 2.9 isn't smaller than 2. What am I doing? That should be 1.9. So 1.9 minus 3 over 1.9 minus 2. That equals negative 1.1 over negative 0.1. Overall, I can see I have a negative over negative, so this is going to positive infinity. And now, as I look at the limit as x approaches 2 from the right, that means I need values bigger than 2, so I'm going to use that upper function. Bigger than 2 means about 2.1. So here I get 2.1 divided by 0.1. That is a positive number, so it's going to positive infinity. So this piecewise function does have a vertical asymptote at 2, but from the left and the right, they're both going to positive infinity. So overall, I can say that the limit as x approaches 2 of f of x equals positive infinity. Oops. Woohoo. And that was a lot of work, but that is all that we're going to do for today. So just reviewing the different scenarios you might see in your homework. You might have the opportunity to just plug in the value and it works. This is what happens when the function is nice and continuous. So you might want to make a little note. Continuous at the point. That's what it looks like graphically. Or in case 2, you might have a hole at the point. Okay, if you get an indeterminate form and have to factor or rationalize, that means you have a hole at the point. Or in case 3, when you get not 0 over 0, this means you have a vertical asymptote at the point. Oops. And so those, just the holes and the vertical asymptotes just means you need to do a little bit more work algebraically to figure out what that limit is.